Today's topic is called sums and differences, and this is important as we move into the next section, which is Riemann sums. But also, the more comfortable you feel with this now, I think the easier it will be in Calc 2 when you get to infinite series. So first, let's talk about summation notation, and maybe I will just begin with two examples. Let's say we add from k equals 3 to k equals 7 of k minus 2, or we add from k equals 1 to k equals 4 of ln k over k. And what are these? Well, both of these are summation notation, but this is a finite sum. So as I was mentioning, you begin with k equals 3, this expression is 1, and then the next one is k equals 4, and this expression is 2. K equals 5, this expression is 3. K equals 6, the expression is 4. And we stop up here, k equals 7, and the expression is 5. Okay, so this is this sum here. Now, what about this one? Well, we add k equals 1 to 4. This is ln 1 over 1 plus ln 2 over 2 plus ln 3 over 3 and plus ln 4 over 4. And because ln 1 is 0, this is literally equal to just the sum from 2 to 4. So maybe I can fit it here. It's a sum from 2 to 4 of ln k over k. It's a little smaller there, but it's the same thing because this first term, the k equals 1 term, is 0. Now, some terminology. K here is the index of summation. And there's nothing special about the letter K. You notice if you write out the terms in the sum, the K does not appear. And so some people call this a dummy variable because it does not appear in the sum. And you don't have to use K. For example, if I go back to this very first sum, this sum, k equals 3 to 7 of k minus 2, we could write this as a sum. Let's say j goes from 3 to 7 of j minus 2. But also, if we just sort of look at the terms, we're adding up the numbers 1 to 5. So this is a sum. Let's say I equals 1 to 5 of just I. And here the index of summation is I, this one is j, and technically going from here to here is something called reindexing, where you start at a different place, but the terms that you add up are exactly the same, right? All three of these are just 1 plus 2 plus 3 plus 4 plus 5. Generally, when we look at sums, we have the following form. So a sum, say k equals m to n of sum f of k, or you might think about it as the following: sum k equals m to n of f sub k. So m, n are integers, and n is bigger than or equal to m. Maybe I should write this: m, n integers, n bigger than or equal to m. And this would be a more general finite sum. Let's discuss an important property of sums, and then I will also discuss a non-property of sums. So an important property, maybe before I mention it, let's see the property in an example. E to the k plus 3 times the square root of k. Well, let's just start writing out some terms. this would be e to the 1 plus 3 times square root 1 plus e squared plus 3 square root 2 plus e cubed plus 3 times square root 3, right? We have 1, 2, 3 terms, 1, 2, 3 terms. Okay, but the property that I want to talk about, you see, I can group this differently. Like this. All I've done is just rearrange the terms, and then on these 3, I factored out a 3. But what is this? This is the sum k equals 1 to 3 of e to the k, and then plus 3 times the sum k equals 1 to 3 of square root k. And this is the property that I wanted to mention right now. It's called linearity, and we've seen linearity of the derivative, linearity of the integral, and this is linearity for sums. And what it says, I will write here, if you sum, I will write it more generally m to n, okay, just because you don't have to start at 1. If you have, let's say, a f sub k plus b g sub k, like this, where a and b are numbers, it's a, the sum k equals m to n f sub k, and then plus b, the sum k equals m to n g sub k. Now, this might seem here, maybe I will box it in purple. Okay, this might seem abstract because I have A, B, F, K, G, M, N. It's so many letters to be looking at. But that's why I started with an example first. Right here was a sum of 2 terms. This would add a constant times it. And then we had just a sum here of this, which is, we see the k, the function of k, and then plus 3 times the sum of this function of k. Okay, and we get that for finite sums just by writing everything out and rearranging. Just as important as understanding what is true or properties that are true is properties that are not true. So a non-property here, which I will illustrate in an example, is if you have a sum of a product, this is not equal to this. Where you multiply the 2 sums separately. And we have to be careful with products. We know, for instance, product rule. If you want to differentiate a product, it's not just a product of the derivatives. If you want to integrate a product, well, you can't just integrate each term separately and then multiply. So products are very different than sums, where you have this linearity for the derivative, for the integral, and for the sum. Here, products, you cannot break it into a product of the 2 sums separately. And let's illustrate this in an example so that we can see that this does not hold. Let's take the sum k equals 1 to 4 of k squared over k plus 1. Well, first of all, let's just do this as it is written. When k equals 1, I have 1 squared over 2. When k equals 2, I have 2 squared over 3. When k equals 3, I have 3 squared over 4. And when k equals 4, I have 4 squared over 5. This is approximately 7.28, okay? Now, on the other hand, let's compute this. okay? And we should not get 7.28, okay, because this is a non-property. So the first one, just adding up k squared, we have 1 plus 4 plus 9 plus 16. And then here, adding up 1 over k plus 1, we get 1/2 plus 1/3 plus 1 over 4 plus 1 over 5. 14 and 16, this is 30. And then this number, you see, we have a half and a fourth and then a third. So this number is bigger than 1. So let me do it this way. Okay. So you see these are definitely not equal. If I add these 4 terms, I get 7.28 approximately. If I multiply these two sums separately, I get a number that's bigger than 30. So this property does not hold. Be careful that you don't use this sometime to try to calculate a sum, because it will lead you to the wrong answer. Now let's discuss some useful formulas that you can use to calculate a sum, and we will use to calculate some sums. The first is if you add from 1 to n of c, c is a number, you add from 1 to n of k, and then we add from 1 to n of k squared. Now, the first one we can just think about, maybe I will do the formulas in purple. We can just think about, because what are we doing here? We're adding the number c up n times. So this would be c plus c plus c, and there are n of them here. And so we see this is c times n. Okay, that was not too terribly bad. The other two are actually quite interesting to prove, and I will just say, if you take math reasoning sometime, or if you have taken math reasoning, you can, and probably will, prove both of these. You can prove them, for instance, by induction. For this one, if we add up the first n integers, that's what this is saying, we get n times n plus 1 over 2. And in this one, we add the squares of the first n integers. We get n plus 1, 2n plus 1 divided by 6. Okay? So like I mentioned, these are formulas that you can prove by induction, but that is not a topic of, induction is not a topic of Calculus 1. So we will use these. And let's do an example now. Here is an example. We'd like to find the sum. Now, we see we have 20 terms, and I certainly don't want to write them all out. And so we will use, I listed 2 of the known sums that we just mentioned. So what can I do here? Well, the first thing I can do is multiply this out. This is k squared minus 4k plus 4. And then we use the linearity of the sum. So this will be the sum, k equals 1 to 20 of k squared minus 4 times the sum, k equals 1 to 20 of k, and then plus the sum, k equals 1 to 20 of 4. And each of these we can calculate in and of itself. So here, it's on the board to remind us, this would be 20 times 21 times 41 all over 6. And this would be minus 4 times 20 times 21 over 2. And this one is just 4 times 20. Now, at this point, I would use my calculator to multiply and add this is equal to 2870 minus 840 plus 80, which is 2110. So this is the value here of this sum. This example, at least this part, looks kind of similar to the last, except it's different because you notice we don't start at 1. And the goal of this problem is to find the sum by reindexing. We can also use this here. So maybe a first initial step is I notice that this is a square. So this is the sum, k equals 6 to 12. This is k minus 5 squared. K minus 5 squared. Now, here's where the reindexing comes into play. Because if you notice at this initial term, when k equals 6, we have 6 minus 5, which is 1. So if we reindex and let j be k minus 5, the sum over the j will start with j equals 1. And this is what we need. For instance, this formula and the other one that I erased that had just the sum of k, those are correct when you start at 1. And so this is why we want to reindex here. Okay, so we have a sum and j starts at 1, and then what's this number here in the sum? Well, when k is 12, j is 12 minus 5, which is 7. And then k minus 5 squared is j squared. Okay? This sum is the same as this brown sum. It's reindexed, and we can directly use this. So this will be 7 times 8 times 15 divided by 6, which is, let's see, we would have 7 times 4 times 5, just canceling off a 2 here and a 3 here. And this is 20 times 7, which is 140. So this sum is 140. Here's another example to evaluate the sum by reindexing. And just like in the last one where we first factored, here I'm not going to factor anything, but I can certainly look here and I see k minus 4, and when I evaluate at this lowest index, I get a 1 here. Okay, so let's let j be k minus 4. But you see I have this k here, so let's solve for k. This is j plus 4. Okay, now this sum will then be a sum. J starts at 1, and then it goes to 30 minus 4, which is 26. And I have 2. There should be parentheses here. Okay. I have 2 j squared plus, well, k is j plus 4. Okay, so here is the reindexing, and the reason why we like this is because, first of all, the sum starts at 1. And then we see here, we're going to have a j squared and a j and then a constant. So this is something that we can use, the formulas that we know. Here we go. Let's break it into a sum of 3. Okay, now I'm ready. This is 2 times here. This will be 26. This will be 27. And then we have 53. then divided by 6, and then plus, this is 26 times 27 over 2, and then we get 4 times 26. And again, I would go to my calculator at this point. We get 12,857. So this is the value of the sum, and we calculated this by reindexing. Now we move on to the differences part of today. Suppose f is a function defined on integers, and then we can define this new function delta f as follows. Delta f evaluated at some integer k, well, you take f of k minus f of k minus 1. This is the difference right now. Just let's do 2 examples. Maybe I will do those in black. Let's find delta f for f of k is k squared. Okay, here we go. Well, delta f of k is k squared minus k minus 1 squared, and we can simplify this. Here, if you multiply this out, this is k squared minus 2k plus 1. And so we have k squared minus k squared, and then this negative distributes across these two. We get 2k minus 1. So this is this difference for the function k squared. So there, you can really study this a lot more than we will in Calculus 1 or Calculus 2. There's something called difference equations, which really just studies this for different functions. It's so beautiful. And well, I remember my first year of graduate school taking a course on difference equations, and I remember how amazing I thought it was. But let's do another example of differences here before we move on. For f of k is ln k, this delta f is, well, it's ln k minus ln of k minus 1. Now this one we can use log properties to simplify. This is ln of k over k plus 1. Oh, k minus 1, excuse me. So this is this difference for the natural log function. And I can just add here, we need that k is bigger than or equal to 2 for this to be defined. Let me just briefly discuss this notion, and it's what happens when you take the sum of one of these differences, delta f. And before I add this, let me just caution or preface more in Calc 2. And this is really when we see the beauty of taking sums of things like this. But let's do an example. Let's take the sum k equals 2 to 9 of delta f of k, where f of k is natural log of k. So we just saw what this delta f was. Maybe I can write it here. 2 to 9. This was ln of k over k minus 1. Well, to really see what's going on here, and generally if I had a sum of a difference, I wouldn't use the simplified form. I would do exactly how we started before I wrote it like this. So this would be ln k minus ln k minus 1. Okay? So let's start writing out some terms and we can see what's happening. Okay, when k equals 2, we get ln 2 minus ln 1. When k equals 3, ln 3 minus ln 2. When k equals 4, ln 4 minus ln 3. And this will continue until we get to k equals 9, where we get ln 9 minus ln 8. Now let's get another color because we can really see some beautiful things happening. Okay, so maybe I should write below k equals 2, this was k equals 3, k equals 4, and then this was the last term, k equals 9. But now let's see what's happening. So you notice here we have a ln 2, and in the very next term there is a minus ln 2. And then we have ln 3, and in the very next term there's a minus ln 3. And then I'm running out of colors up here, but we have an ln 4. And in the very next term I will have a minus ln 4. And then we get to the second to last term, we will have an ln 8, and it will add to 0 with this minus ln 8, okay? So all of this stuff in the middle is adding to 0. What will not add to 0 will be, we have this minus ln 1. Well, ln 1 is 0, but it doesn't add with anything else, so maybe I will write it. And then in the very last term, we have an ln 9. And everything else had a mate, sort of coming from another index that it added to 0 with. And so you see, this sum was quite straightforward to calculate once we wrote it as a difference. So this is, we wrote it as a delta f, and we got just ln 9. This is something called a telescoping sum. Maybe I'll write that underneath. And it gets its name from these old-fashioned telescopes where you stretch it out and then you can push it back in. At least I think so. But you see it's stretched out, but really it's just all the middle stuff adds to 0, so it's very short. I think that's where it gets its name. And this comes up even more in Calc 2, where we not only have a telescoping sum, we have something called the telescoping series. But perhaps we will close today with one more example of a telescoping sum. And here it is. Just as a comment, this part here, this is delta f of k, where f of k is 2 over k plus 1. Okay, so this is a sum of a difference, and this will be a telescoping sum. Let me put the parentheses. Okay, here we go. So we just start writing out terms, and then we see all the middle stuff that will cancel, and we have to see what's left over at the end. So when k equals 3, we have 2 over 4 minus 2 over 3. When k equals 4, we have 2 over 5 minus 2 over 4. When k equals 5, we have 2 over 6 minus 2 over 5. Maybe I should be writing these. This was k equals 3, k equals 4, k equals 5, and we'll do one more. K equals 6, we get 2 over 7 minus 2 over 6. And then let's jump to the last one, which is k equals 10. We get 2 over 11 minus 2 over 10. And just as I said, this one is k equals 6 and k equals 10, okay? So here we see some of the terms written out. And now maybe I will just put with green dots, just use only one color this time, what adds to 0. We have 2 over 4 minus 2 over 4, 2 over 5 minus 2 over 5, 2 over 6 minus 2 over 6. The 2 over 7 will add to 0 with something in the next term. And finally, this 2 over 10 will add to 0 with something in the previous term. And so we're left here with minus 2 over 3 plus 2 over 11, which is minus 22 over 33 plus 6 over 33 minus 16 over 33. This sum is negative, and it makes sense. If you look at any one term, 2 over k plus 1 is smaller than 2 over k.